guys, this is Assistant Professor Mishdas here from LG Institute of Engineering and Technology. Now in this session we will discuss the new diode, that is a Zener diode, and this is also said as a spatial diode. Why spatial diode? Let's discuss. So basically, let us understand what is a Zener diode. A Zener diode is a special type of diode designed to allow the current flow in the backward when the Zener voltage is achieved. Now usually what was the problem in the PN junction diode? In forward diode it was definitely conducting very well, okay, but in reverse bias it was working as an open switch, or it was not allow the electric current to flow through it, okay. So the charge carriers were not allowed to flow in the reverse bias, but exactly the reverse. In Zener diode, it is designed in a special way that it operates in a reverse bias. So it is named after the Clarence Zener, on the physicist who has actually discovered the Zener diode. And symbol is almost identical except that anode is triangle, but instead of that straight line you have got that Z, and Z stands for nothing but the Zener. Now how it looks practically? Practically it is identical as orange side is the anode and the cathode, that is nothing but the black line. So it is not looking, see, Zener diode is looking very much different than the PN junction diode. It's very easy to recognize it because it's orange in color, and that orange color is actually denoting the anode, and the straight black line is the cathode. So after that, how is Zener diode formed? So basically a Zener diode is formed by diffusing a highly doped P and N type semiconductor together. Now the thing is that doping is done in the higher order. Just compared to the PN junction diode, again it is a P and N type and diffused together. But one word is extra there. What is that one word extra? That is nothing but the doping is very high. And doping process is nothing but the adding on impurity more. So what was happening, as we were adding the impurity in P, we are getting extra holes, and in N type we are getting extra electron. So the word more doping or highly doping means in P type you will get extra holes, and in N type you will get more extra number of electrons. That you can see in the diagram. See, now in P and N region you can see that it is highly dense. Highly dense with what? Highly dense with holes on the P region, okay, while doping is very high. And similarly in N region also doping is very high, so electron density is very tagged to each other, okay. So the almost space is very less, and because of that only the depletion region is very thin, okay. Now why that is very thin? Basically what happens in N region, due to the diffusion process, it tends to move from N region electrons to the P region. But the problem is P region is already tagged with the hole so much amount of space to allow the electron to reside there, okay. Vice versa, when the holes are in so much amount in density, again there will be a diffusion thing process would be there, of course, but when it moves there is no much space available in the N region to reside. That's why whatever the small amount of space is there, it is utilized, and a small thin depletion region is created, okay. So compared to the PN junction, the depletion region is extremely narrow in the Zener diode, okay. So now how the working principle of Zener diode works. So first we will go with the Zener effect. So now the Zener effect will be justified as it is a type of the electrical breakdown that occurs when electric field enables tunneling of the electron from valence to conduction band, leading to a large number of the minority carriers that suddenly increases the reverse current, okay. So actually the reverse current and Zener effect is there into the picture, okay. What is happening because of that reverse current? What is happening, that reverse current actually flows through the Zener diode. Now how it is happening, let's see in the working of the Zener diode. So first we will go with the avalanche breakdown. What is avalanche breakdown? As Zener is having heavily application in your reverse bias, we will discuss only the reverse bias conditions. So in avalanche breakdown, it generally takes place in the lightly doped PN junction diodes, okay. Second, the PN junction diode cannot regain its original position after the breakdown and its burn off. So once the avalanche breakdown is occurring in the PN junction, it will be not back into the normalized, okay. And second, after it is not normalized, it will be not utilized again. Why? It is completely burned off. After that, the avalanche breakdown occurs because of the collision of the free electrons with the atoms. Now how it you can see that in the reverse bias, P is connected with negative terminal, N is connected with the positive terminal. Okay, depletion region width is comparatively high. This all we know. But now what happens? In P time, you have got the minority electrons still present there. So what happens? This negative terminal that is connected with the P type will get energized this minority electrons, and definitely all holes would be connected or get attracted towards this minus terminal, but electron will be energized and it will move towards the depletion region. So as it moves towards the depletion region, what will happen? It will be more energized. Why? Because it is not only moving, but as you are increasing the voltage of the battery, so that negative voltage is actually energizing that electrons at a very high level. So when it is moving, its velocity is very much high, and when it gets dashed, now see what is in the depletion region. Ultimately, electrons. So when it dash with this high velocity, it's get collide, and because of this collision, what happens? The another electron is also taken out from its position, and this is not happening for the single electron. It is happening for the n number of the electron. So you can just imagine that n number of the electrons getting dashed, collide, and that much n number of electrons are generated. Again, this 2n number of electrons are again colliding, and so on. So this is a chain reaction starts. But we know that whenever there is a collision, there will be always generation of heat. Okay, so now as you are increasing the reverse voltage slowly and gradually collision increases, and after certain collision, what happens? This free electron starts flowing instead of the barrier. Though the barrier is there, that still it will be flowing, but once you increase more, this what will be that? Because of this collision, there will be heat, and your PN junction gets burnt off. So this is going down, and that is the only reason it doesn't return to its normalized position as it has been burned off. Now let's see what is happening. We are just concluding it. So first we are providing the reverse voltage increases. So because of that, what happens? The kinetic energy of the carrier increases. Okay, so carriers we are talking about on the p type, for example, it would be of electrons. So as they are moving, now electrons collide with the atoms of the crystal, impart the energy to the valence electron. So once the valence electrons are taken out, now what happens? This energy breaks the covalent bond, generating more minority carriers, as we have discussed. So after that minority carriers, this cumulative effect continues and leads to the large flow across the junction. Okay, so this will get you the avalanche breakdown. Now it's another part, that is what is a Zener breakdown. So in Zener takes place in the heavily doped Zener diodes only. That's why, of course, that's why it is known as a Zener breakdown. After that, the Zener diode is actually said to work after this breakdown. So after that breakdown, only Zener diode's application is coming into the picture. The Zener breakdown occurs because of very strong electric field across the junction. So these are actually the takeaway points. Now similarly, we will see how the Zener breakdown is occurring into our devices. So now we are taking a Zener diode. Depletion region is very narrow. Now as you increase this electric field, now we know that electric field is equal to V by D. D is the depletion width. So now as depletion width is very less, what will happen? This electric field, as you increase the voltage, what will happen? Similarly, electric field will also increase across it. Why? Because on that depletion width is extremely low. So now as a strong electric field is generated, what will happen? It will break down the covalent bonds. And as it breaks down the covalent bond, you are getting the high value of the electrons that are actually flowing. But what is happening here? Because of the external field, that is electric field is generated, because of that the valence bands are coming out and it is breaking from its covalent bonds. Okay, so as you increase the battery voltage, electric field increases, and so much amount of the electric electrons you are getting. Now as you switch off the battery down to the normalized position, again the electric field is reduced and everything would be in normal position. Okay, so this is what is happening in the Zener effect. So now we will again conclude it. So how we are concluding? Reverse voltage increases. So because of the reverse voltage, we know that the electric field at the junction increases. So that increases. So a strong electric field, what would be doing? It would be breaking down the covalent bonds, and as covalent bonds electrons are breaking, what we will be getting? We are getting the large number of the minority carriers. In our case, is nothing but the electrons. So after that, this cumulative effect again continues and large flow of the current is there throughout the junction. So this is your Zener breakdown. Okay. So now we will go with again the IV characteristics for the same. Now there is always we are discussing in the reverse bias, that is Zener diode, and it will be working in the reverse bias as a closed switch. Okay. And this is the forward bias condition in which it will be operated in the forward bias. So what is the myth? See, Zener diode occurs normal diode, as a normal diode is occurring, it will get in the forward direction only. It is not that the Zener is not operating in the forward bias. It will be operating as a normal diode only. But the main takeaway is in the reverse bias. See, this is the Zener breakdown. It is comparatively very sharp. Okay. And because why it is very sharp? Because as you are increasing the battery, electric field is generated. Because of that, instantly the covalent bonds are breaking down. But what is happening in a normal BM junction diode? Slowly and gradually, as the electrons are gaining velocity, they are dashing, and slowly and gradually chain reactions are starting, and on that basis of chain reaction, you are getting the high number of the electron. So if you comparatively see the graph, Zener has got sharp and Avalanche is comparatively, you have got the slow. Okay, so this is the basic graph of the Zener diode in the forward and the reverse direction. So now the Zener breakdown, we can conclude it is a sharp in nature. Avalanche is comparatively gradual in nature because it is happening of the chain reaction, and that is happening because of the instant electric field developed. So now we go with the applications. Now as a voltage regulator. Now what is a voltage regulation? Means controlling the voltage. Now we know that if you are setting Zener diode at particular voltage of, for example, 5. So its operation would be starting after 5 only. Now it is using the wave shaping circuit also to the peak limits upper and the lower. We know that how the shaping is done with the help of the clipping of the circuits. Use of the meter protection to prevent against the damage of the accidental overload. We know that accidental overload, what would be that this Zener diode is connected in such a way that when the extra voltage is there, it would be draining out those all extra voltages. Hence, it would be saved from the damages. So this was all for the Zener diode. See you in the next lecture.